In this video, we're going to learn how to do basic Lewis structures of molecules. So I'm going to start with a quick review of bonding. Remember when we first talked about bonding at the beginning of the year, we said that atoms will bond to become more stable. They want to have a full outer shell to do this. We call that attaining a noble gas configuration. This usually requires 8 valence electrons. There are 3 main exceptions. Hydrogen only needs 2. Boron only needs 6. And then we also have something called expanded octets. We already talked about this. They bond to become more stable. So our type of bonds that we're going to focus on here are ionic and covalent. We're mostly going to focus on covalent. We also talked about metallic, but those aren't really important here. So in an ionic bond, we would have a metal and a nonmetal, and electrons would be transferred. In a covalent bond, you will have all nonmetals, and electrons will be shared. Lewis structures that we're going to be starting today, Lewis structures of molecules, are all covalent compounds where the electrons are shared. Before we get to Lewis structures of molecules, I want to review Lewis structures of atoms. So when we did this, it was a very long time ago. When we did this, we looked up the valence electrons for each element. So on our periodic table, we look up the element and see how many valence electrons. So fluorine is in group 7A, so it gets 7 valence electrons. So we have 7 valence electrons. To draw the Lewis structure of just fluorine, we would put F in the middle, and then we would put 7 dots around it to represent those 7 valence electrons. For carbon, when we look carbon up on the periodic table, carbon is in group 4A, so it has 4 valence electrons. So we would show carbon with 4 dots around it. And remember, we would put 1 on each side before we double them up, because if you have 1 electron with an empty space next to it, that means we can form a bond. So based on this, we would expect carbon to form 4 bonds and fluorine to form 1 right here. Oxygen has 6 valence electrons, and hydrogen has 1. So that is the valence electrons of just an atom. It is going to relate to Lewis structures of molecules, and valence electrons are very important for that. So in your notes, you have a set of rules. These are the Lewis structure rules that we are going to follow. Okay, so follow along with this as I am doing the problems and the structures in the slides. So the first one I'm going to start off with is PBr3. Step number 1 says to count the valence electrons in the molecule. So what you do for that is you look up the valence electrons for each individual atom. So here in this problem, we'll have P and Br. P gets 5 valence electrons because it's in group 5A, and Br gets 7 because it's in group 7A. So for P, we have 5 valence electrons, and the subscript on P is a 1. So we'll multiply by 1 phosphorus. Br gets 7 valence electrons, but we have 3 Brs, so we're going to multiply that by 7. And that gives us a total of 26 valence electrons. I'm going to keep a running tally off to the side because at the very end, we have to have exactly 26 electrons in our picture. We cannot have any fewer or any more. Next step says to pick your central atom. And then A, B, and C below step number 2 tell you how to do that. 2A says that hydrogen and fluorine will never be the central atom. We don't have hydrogen or fluorine here. So that means we go to 2B. You have to follow these A, B, and C in order. B says that if carbon is present, it will usually be the central atom. For purposes of our class, it will always be if it's there. But we don't have carbon here either. So then 2C says the central atom will be the least electronegative. So to find the least electronegative, you can use your periodic trends knowledge. You can also say, okay, fluorine, we know from Unit 5, is the most electronegative. So what I tell students to do sometimes is count the boxes from fluorine to the 2 elements. So here for phosphorus, you would have 1, 2, 3 boxes to get to fluorine. You can't go diagonally in this one. But if you went this way, 1, 2, 3, it's always 3. For bromine, you're going to have 2. The least electronegative is going to be the one further away from fluorine. So sometimes I'll have students write that in on their notes. If it's not already there. Sorry, I put it there. So our answer here is going to be phosphorus for our central atom. Then you arrange all of your terminal atoms around your central atom. And we have 3 bromines, so we draw all 3 of them. Next, we connect our terminal atoms to our central atom. And that is a bond. Each bond is worth 2 electrons. So here we have 1, 2, 3, 4, 5, 6. Anytime you draw an electron, you go over here and subtract it. So that way we can keep a running tally, and at the very end, we know we have exactly 26. Now, the first thing lots of students want to do is not keep that tally. That will run you into trouble quite a bit. So try not to take a shortcut here. Next step is to put 3 pairs of electrons around each terminal atom, as long as that terminal atom is not hydrogen. I drew 18 dots, so I subtract them. And then the last step is to put the 2 remaining electrons on the central atom. Last thing you do is make sure all of your atoms are happy. All that means is that they follow the octet rule. So we go through and count how many electrons are surrounding each atom. 1, 2, 3, 4, 5, 6, and then remember this bond is worth 2, so 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So now let's look at phosphorus. We have 2 for phosphorus, but then bonds are always shared because this is a covalent compound. So even though we already counted this bond for bromine, we can also count it for phosphorus, and same for the other 2. So we end up with 1, 2, 3, 4, 5, 6, 7, 8. So all of our atoms follow the octet rule. This one is done. This structure is done. So now I'm going to do hydrogen. I'm going to start with the same idea. Oxygen gets 6 valence electrons, and we have 1 oxygen. Hydrogen gets 1 valence electron, and we have 2 hydrogens. So we have to have 8 in our picture. Rule 2A says that hydrogen and fluorine will never be the central atom. So I'll put oxygen in the middle, and then the hydrogens around it. And it doesn't matter where you put the terminal atoms as long as they're around it. Same for PPR3. I then connect them and subtract 4 because I drew 2 lines and they're each worth 2 electrons. Next step says to put 3 pairs of electrons around each terminal atom that is not hydrogen. Both of our terminal atoms here are hydrogen, so we can skip that step. Then we put any remaining electrons on the central atom. And then we check to make sure they all follow the octet rule. Now you'll notice that hydrogen doesn't have any dots, so it only has 2 electrons. But if you look up on your notes, it is one of the exceptions. It only needs 2 electrons, so it's good. And then we have this hydrogen with 2, and then oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Now we'll do CO2. Carbon gets 4 valence electrons. We have 1 of them. Oxygen gets 6, and we have 2 of them. So we end up with 16 valence electrons. Rule 2a says hydrogen and fluorine are not the central atom, but we don't have those here. 2b says carbon will be the central atom. I'll put my oxygens around it. I then connect them and subtract 4. Next step says to put 3 pairs around each terminal atom that's not hydrogen. And I drew 12 dots. But now it's important to go back and make sure each atom is following the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. So that oxygen is good. 1, 2, 3, 4, 5, 6, 7, 8. That oxygen is good. But look, carbon only has 4. 1, 2, 3, 4. Now, a lot of students will say, well, carbon only needs 4. It's in group 4A. That's not true. Carbon starts with 4 because it's in group 4A, but the whole point of bonding is that they all get a full outer shell, that they all follow the octet rule. So carbon doesn't get to stay with 4. It has to have 8. So what you can do is take one of these pairs on oxygen, because remember that oxygen that has the lone pairs, but a bond is also made up of 2 electrons. So we can take those 2 electrons and make them a bond. Now that bond is shared between carbon and oxygen. So now oxygen still has 8. 1, 2, 3, 4, 5, 6, 7, 8, because each line is worth 2. But carbon now has 6. So if we do the same thing on the other side, now we have everyone following the octet rule. So you might also notice that we could have done a triple bond over here, and you can have triple bonds. You can have single, double, or triple, nothing higher. And there is a lot more complicated rule as to why that's not the preferred structure. For now, just know that atoms will be symmetrical if at all they can be. Okay, so rather than having a triple bond over here and single over here, we would prefer to have a double on each side. So that is our structure. And that's the basic Lewis structures. So now we're going to add on to that just a bit. For polyatomic ions, it is the same basic idea, except you have to adjust your valence electrons for the charge. You can do that at the very beginning, and then you never have to think about it again. So for SO4, when we count up the valence electrons, S gets 6, and we have 1 of them. And then oxygen gets 6, and we have 4 of them. And then adjust for the charge. So 2 minus, remember, means we add 2 electrons. We learned that a long time ago. If it was 2 plus, we would take away 2 electrons. So all we have to do for that 2 minus is add the 2 electrons at the very beginning. And now we can just go about our business and do the structure exactly the same way. So S is going to be our central atom. The O's will be around it. We'll connect them. Subtract our 8. And then put our 3 dots, our 3 pairs around each terminal atom. And then make sure they're all following the octet rule, which they are here. At the very end, you usually, for polyatomic ions, will see brackets and then the charge copied on the outside of those brackets. And then the last thing I want to talk about in this video is something called a resonance structure. A resonance structure happens if you get to a point in your Lewis structure and you need a multiple bond, but it doesn't really matter where it goes. So it's not the same as what we did before when we said for CO2 we wanted it to be symmetrical. Let me show you for O3. For O3, we're going to have 3 O's. Our valence electrons are 18. We connect our 3 O's and subtract our 4. Then we put 3 pairs around each terminal atom. We have 2 left, so we put them on the central atom. But if you look, our central oxygen here does not have 8. It only has 6. So we could take a double bond, we could take a pair here and make it a double bond. Or we could take a pair here and make it a double bond. And it really doesn't matter because we don't need 2 double bonds. We just need that 1 double bond. So if that happens, what you have to do, if you get to a point where you're like, it doesn't matter where I put this, you want to put it in all the possible places, show all the possible places that it can be. And that's called the resonance structure. So I would put it on this side, and then I would also do it on the other side. And then you put a double-sided arrow, and usually you'll put brackets around them. But you definitely need the double-sided arrow to show that it doesn't matter. You can have both of those structures, or sometimes even 3 structures. And that's all we're going to do for Lewis structures here. We'll also learn about expanded octets, but that will be in another video.